OmegaClaw system, at some level, it's accumulating knowledge across all the different research projects I'm giving it. They're all about Hyper-Realm plus predictive coding for AGI. It's able to deploy knowledge from one project to sort of help give suggestions about another project.
There's lots of cool opportunities for building new AGI components and systems in FabricPC and with OmegaClaw as well, as you'll hear from Patrick, how really cool integrations are happening there as well.
And for us, for SingularityNet, there's also the wider picture of building AGI-ish systems that integrate various cognitive systems into one thing that can then essentially operate on its own autonomously. OmegaClaw is essentially a continually operating agentic architecture, which is built inherently to run in a lifelong session.
I'm trying to build that out in a way that possibly could agglomerate toward actual AGI.
Hello and welcome. Greetings, Singularitarians. Welcome, BGI adventurers, and all of our AGI conference attendees and researchers. Welcome. Thank you for joining here today for another Tech Tuesday. It's going to be a fantastic episode. It's going to be so interesting. We have an opportunity to dive deep on two of our tools, one of which we've covered before here, and one of which this is the first time we get to talk about and unpack in this space. And both of these tools are being presented here today in the context of our BGI open build. So this open build is just an opportunity, an event for AGI researchers, enthusiasts, tinkerers, independent researchers all over the world to get their hands on AGI research tools. These two tools enable anybody to participate in the next level of AI intelligence, which is why we're so excited to bring them here today. So today's event kicks off 2 weeks or 10 days actually, where we're going to have an open space available for anybody who wants to use these tools, research AGI, progress motivation systems, attention systems, cognitive architectures, self-models, world models, whatever your flavor of AGI curiosity is, we have tools. Neural networks that go beyond LLMs, of course, with FabricPC. We have tools that enable everybody to bring you beyond the current limitations of AI and contribute your part to the emergence of AGI. So today's the kickoff. You can register with us for this open BGI build time. We'll have a couple of events throughout these 10 days where people can participate, ask questions, share what they're building, highlight the directions that they're looking in and what they've discovered with these tools, and then submit projects. And these projects will get highlighted at the AGI conference by our researchers. So this is an opportunity for everybody to get involved and have their insights taken in and boiled up. We've already had some great results from this. We just finished a BGI sprint a few weeks ago, and at least two of our projects, one our winning project and another project that contributed, have already been incorporated with some of Ben Goertzel's own AGI research with OmegaClaw. So that's Larry Greenblatt's Threadkeeper and Mesto's Goal Chainer. And now we're going to build on that and build out even more. Now we have a couple of options as well. Looking for a community to build cool things on our two tools. We're going to start with FabricPC, which is it's an infrastructure, it's a tooling, a library for building fundamentally different approach for how neural networks learn. We can see worldwide that LLMs, they're hitting the top of their S curve, and it's time for the next innovation that takes neural networks and neural learning further than it has before. Predictive coding is our guess, our line of research towards that direction. And FabricPC is the tooling that anyone can get involved with all of the innovations that will happen there to make it scalable, robust, and take on the mantle of the next neural network architecture. And then OmegaClaw, which provides a platform to integrate cognitive architecture for adaptive intelligence. This is a neural symbolic agentic harness running on the power of LLMs, but utilizing meta for self-reflection, utilizing atom space for persistent memory over time, non-context window-based memory, PLN, and tools for retrieval and attention, memory mechanisms. Really exciting stuff. So I won't go on any further. I'll let our researchers do the talking for us. So we'll kick off now with Matthew Barrand, who built the FabricPC library. And can you dive in both about what FabricPC is, how people can use it, and how this points to the next level of learning for neural networks?
Hi, Haley. And thank you. It's great to be here with everyone. Yes, FabricPC is a library for predictive coding training of neural networks, similar to how PyTorch is built for training neural networks with backpropagation. Predictive coding is another algorithm in the larger space of how we train neural networks. And what it does is recast the entire framework for how a model is trained from chain rule propagation of errors from the output all the way to weights, the way backprop is done. And in predictive coding, it reframes this and says, what if we treat this kind of like a physical system and use an energy-based framework to measure an error at every layer of neural activation throughout the entire model, have an energy functional for the error for each layer, and then minimize the global energy of the network, allowing it to settle during an inference phase to find the optimal activations of each layer. When we do this, it opens up new possibilities for network architectures, allows us to naturally handle recurrency and open up new avenues for associative memory built into deep learning networks. So we're very excited about the prospects that FabricPC offers for building with predictive coding. Some other advantages to predictive coding besides the architectural freedom of being able to work with arbitrary graph structures and recurrency naturally, the things that are difficult to do in backpropagation for people working on the overlap of neuroscience and machine learning. It offers biological plausibility where a predictive coding algorithm, while it doesn't work the same way the brain does, it was brain inspired as a potential theory for how cortical processing works. It learns locally in a Hebbian-like fashion. So each node learns locally according to its error and the layer next to it. So being able to run a network with local learning is also a unique advantage of predictive coding. Another reason why we're really interested in investing in predictive coding throughout SingularityNet is that we also see that this is a future for scalable AI that's extremely energy efficient and works well with distributed computing that's coming soon in neuromorphic hardware that's currently in development and research. While backpropagation does not fit neuromorphic hardware or non-von Neumann compute architectures, predictive coding does fit those much more naturally, particularly the analog variants of neuromorphic computing. And we know the brain uses very little power in order to compute compared to the data centers that were crunching many billion parameter models. But with a similar scale of number of neurons, the energy requirements for this could be reduced dramatically. That has huge implications for our power grid and being able to scale AI in a way that's humanitarian and earth friendly, as well as simply being practical for scaling up the power of these AI systems and building AGI that's accessible to everyone.
It's so important, all these issues, right? This both aligns with our commitment to BGI and bettering the planet, and as well as our ideas of decentralization and enabling local learning and local compute and multimodal processing, continual learning are all possibilities in this architecture. We had a hackathon with some of our ICOG developers in Ethiopia. Can you speak a little to how they brought forward and built new capabilities for this tool?
Yeah, that's a wonderful example of how community could get involved. And we did this internally with our ICOG researchers based in Addis Ababa. And we had about 4 teams and about a dozen members working together to go from new concept to PRs to FabricPC in just half a day. And in that hackathon, we had some wonderful teams building improvements to our predictive coding transformer architecture that's demoed in FabricPC, as well as natural gradients. So using the incompressible Navier-Stokes equations to produce more accurate gradients, and a number of other projects. Now we have new initiatives being developed within SingularityNet that are on our roadmap for our research as well as FabricPC integration, including modern hop field networks, so a very dense associative memories, and also new work in transformers, doing PC trained transformers and building upon and also fine tuning existing transformers using predictive coding and integrating them seamlessly with the atom space of our SingularityNet knowledge graphs. There's lots of cool opportunities for building new AGI components and systems in FabricPC And with OmegaClaw as well, as you'll hear from Patrick, how really cool integrations are happening there as well. And I think we're going to see more and more of this integration of neural and symbolic happening. And FabricPC provides an excellent library for training neural networks and doing that integration with symbolic structures. I would be happy to also dive into some brief demos and walk people around FabricPC a little bit so you can see how you can play with it yourself. So first, what is FabricPC? It's an open source Python JAX library that's SingularityNet infrastructure built by SingularityNet, intended for scalable, high quality production level research. And this is in its early phases, but it is in a place that is ready and mature enough for the community to play with. We welcome you to work with it, tinker, and submit PRs for improving the library, as well as share with the community what you're able to build with FabricPC and perhaps even with OmegaClaw in connection with it. I even tap with developing something in FabricPC. So this is ASI Alliance infrastructure. It is open source under the MIT license, the GPU and multi-GPU ready, so it runs efficiently as far as predictive coding on current hardware. And in our roadmap, we have even more cool things coming down the pipeline in the next few months for speeding up predictive coding dramatically for very deep neural networks. The library works by abstractions of nodes, edges, and updates. So if you go to the README, installing it is very straightforward. Choose your installation for CUDA according to your hardware and drivers. And then some things that it makes really easy to do versus other predictive coding repos that are available. It seamlessly handles auto differentiation at the node level across arbitrary graph structures. So it removes a lot of the boilerplate that you typically have to do with predictive coding, and allows you to get straight to developing new models and developing new components to integrate into your networks. And you can start with running a quick demo in the FabricPC examples folder, MNIST demo. And here we have Python demo. And this will run in just a matter of a minute. Consumer GPU hardware.
And this is what I love about it. I've run it, right? It's really accessible what you've built here so that anybody can begin to play with this next level technology.
This is running the classic multi-layer perceptron with two hidden layers and a classification head, softmax and cross entropy, energy, and it just completed, runs at 98% accuracy. And what's fun about this is that defining this network is very familiar for people who are working in other common frameworks like PyTorch or Flat. And here, in order to create a graph, we set up the nodes. So we have an input node, which we just set as identity that clamps the input data, and then a hidden linear node with the shape of the tensor, another hidden node with the shape of the tensor, and then an output linear node with cross entropy energy. The energy of the intermediate nodes is automatically handled, and you can override any defaults by setting configurations in the node definitions. Then to create a graph, laying out the nodes that we've defined, and then drawing edges between these nodes in a directed graph, and then mapping the X and Y data of the data loader to those input and output nodes, then telling it which inference algorithm we're going to use. FabricPC also makes it really easy to compare and validate experimental models using backpropagation as a point of reference if you want to compare predictive coding to the backprop solution. It runs on exactly the same graphs and just changes the algorithm used to train. So there's no code duplication in order to do that kind of validation or checking. And then we can also do other really cool things, like we can have cyclic graphs where the input pixels come into a hidden layer and go to a hidden 2 layer, then having a backward connection that then feeds as an input into the hidden 1 layer. And these recurrency cycles are very naturally handled in the inference phase of predictive coding. We also have a demo for hop field network. And the really cool thing here is that hop field is a composable element in FabricPC. So it's a node just like any other node. And here we have a demo comparing a straight MLP of 2 hidden linear layers before a classifier. And then the hop field variant, we can replace one of those hidden linear nodes with a hop field network, which then learns what sort of memories are useful as features to the task head layer.
It's incredible how robust you've made this library and how easy it is to get started with. So before we wrap over to OmegaClaw,
Is there anything in particular you'd point community at as a place to input or a place to research or some place to get started with making improvements or building something interesting on FabricPC?
Yep. Start with running a few of the demos, and then our transformer demos are actually active research. So check out the transformer V2 demo and run that, experiment with different variations on the architecture. You can also modify the node definition itself. In FabricPC nodes, we have the definition for each of these nodes. The key thing there is defining the forward method, which has all the computations for how inputs are transferred to predictions for that layer. Beyond that, welcome you to check out our repo in GitHub.
Thank you very much, Matthew. It's an incredible project. I'm so excited to see what the community can build and look at. In time for the conference, we'll have quite a lot of discussion on all of this.
Welcome everyone to come build with us and open PRs on the repository.
And we can connect anybody who wants into the Mattermost channel on Learning FabricPC. And that other thing that's amazing about both these tools is how much modern LLMs can help with both of them. So even if you're unfamiliar with everything here, with predictive coding and everything, LLMs can help you understand what predictive coding is, how to use it, how to use this library, how to go through the demos, ideas to augment it. It's pretty crazy. Thank you so much, Matthew. I'm going to transfer over to OmegaClaw now, our second AGI-ish research tool. And, here we are. We're looking at OmegaClaw as a cognitive, start of a cognitive architecture built on LLMs, start of using the LLMs to power adaptive problem-solving agents, and as an AGI research tool for anybody to explore their flavor of what they're curious about in the world of AGI. So, Patrick, please take it from there.
Thank you. Thank you, Haley. Hi, everyone. So today, as Haley mentioned, we will also discuss OmegaClaw, which has been quite a big effort at SingularityNet. It's basically a agentic system, as many have seen also from using various coding agents and so on. The LLMs nowadays are able to call tools, and you can essentially build systems that act and do things with your computer. And for us, for SingularityNet, there's also the wider picture of building AGI-ish systems that integrate various cognitive systems into one thing that can then essentially operate on its own autonomously, take user tasks and get them done. And all of this, of course, needs some advanced machinery, like it needs long-term memory so that the agents remember what's going on and what has happened and what it has already done and so on. And I also prepared a presentation. I will try to share my screen. OmegaClaw is essentially a continually operating agentic architecture, which is built inherently to run in a lifelong session. When you have used coding agents, they are essentially session-based. And in OmegaClaw, we try to blur the session boundary a bit to make essentially a system that runs continuously and also not in a request-response fashion, but the idea is that this agent is always active and works on tasks that are related to the tasks you gave it. So even when it has done your tasks, ideally it should work on related things that might provide value to you. And that is essentially a continual way of operating. And for us at SingularityNet, there's especially this idea that we integrate various cognitive components. For instance, the system is programmed using the meta language, which meta language is essentially a language that can do self-modification effectively. So the agent can essentially inject code into its own system and can execute it, can build doors in meta, can execute them, and can also operate various reasoning tools like null and PLN, as we will see. But at the heart of the issue of having an agent that runs continuously is it doesn't live in a closed world. It's not, there are no session boundaries. Ideally, it should just continue operating, and that is actually a hard engineering challenge, because essentially you need to satisfy the finite context capacity which LLMs have, and you need to be able to judge which memories are more important than others. So it's essentially trying to build a system that operates under the assumption of insufficient knowledge and resources. And some of who have followed previous research on non-axiomatic reasoning system, that has also been a working assumption there. agents nowadays face the same problem. You have finite context window, you have incomplete evidence, yet your agent needs to make decisions. It needs to learn about the world and needs to update its beliefs about the world. And all this comes with time pressure. You want your agents to operate and to get your tasks done. So what we have so far, here it still says OmegaClaw because that was initial project name before we named it OmegaClaw and created the public release. It's essentially an orchestration agent that is meant to coordinate the use of various cognitive components, including probabilistic logic networks and also non-axiomatic logic using one component, but also different hyperrun components such as economic attention allocation, and having these different cognitive components operate together has always been a challenge. It has traditionally in the OpenCog project been a matter of having the so-called cog server that coordinates the different components. But in this case, we use a agentic system where the LLM decides what kind of components to invoke, including reasoning tools. And the way this looks like, it can be seen like a loop structure where you have perception, and the perception can be user messages, but it can, as we will see, also include multimodal input that creates the context for the LLM or VLM, which then has to decide which doors to invoke, which can also be cognitive doors like reasoning doors, which provide conclusions, which it can then, again, via door calls, store in long-term memory or retrieve related information from long-term memory. It's essentially a continual loop that just keeps operating. And even if there's no user message, agent might still be active. And if you touch a camera to it, for instance, it will just be able to keep working and see what's ongoing in the scene. What's interesting is if you look at the entire system state of the system, you see there are different kinds of memories that are part of this agent. They can essentially create what is called a bin state that is more like for working memory, where the agent keeps track of task progress and partial results that have been recently generated. There's essentially, and there's the episodic trace, which captures everything that has happened, not everything, but a certain limited window of events that happened, depending on configuration, say the last 10 minutes of observations and door calls. Also, there's the long-term memory, which is a semantic memory. So the agent can decide to store certain information in the long-term memory for later retrieval via embeddings. So it can essentially decide to store something in its memory and then later to retrieve memory items by querying it. And what has also been interesting more recently, since we have all the symbolic components also in the Hyperrun project, like probabilistic logic networks, it's very natural to also allow this agent to build atoms and to have a symbolic representation in its memory, which we call the atom space. This memory space we call atom space, and the agent can then store symbolic expressions there and operate efficiently over large symbolic spaces using these reasoning tools. And additionally, like other agentic systems, it can also work with files and external scripts and invoke software that is external to it. But for the reasoning side, it's essentially another type of door call. So it can decide to invoke a meta command that just matches the inference rules which it has available on a set of premises, where it can also pass a certainty value. And then as a result, it will get back a statement or multiple derived conclusions, which it can then selectively decide to remember using its memory operations. That's essentially how reasoning tools are currently integrated in this agentic system. And this combination of reasoning tools is also quite unique in OmegaClaw and allows it to perform a reliable form of reasoning that can be traced in detail to essentially see how it came up with its uncertainty estimations. And we have also recently published a paper that shows various memory results on, in this case, long memory, showing that the system is quite effective in its long-term recall, closely trailing the state of the art here, even though we have a relatively simple memory system that gives the agent a lot of freedom of how to store memories and how to retrieve them over multiple agentic cycles. Also, what has been surprising with OmegaClaw, that's especially AGI relevant, it has been able to solve various arc challenges, even though there is zero arc-free specific code. in OmegaClaw, it was still able to solve various arg-free challenges. And as you see there in the bar plot below, the amount of steps it takes, it can vary greatly. So it doesn't always get lucky to find the right coherences in the environment right away. So sometimes it's quicker, sometimes it's slower. It also depends a bit on luck, but still what has impressed us is that it's able to conceptualize the environment on a quite high level and is able to extract what matters in order to accomplish various tasks. So far, it's of course, it's not yet guaranteed that it can solve or arg-free levers, but it has at least solved a significant fraction of it already, which was unexpected since we didn't provide domain-specific code for that. What also has been quite interesting is the multimodal capabilities, since we can essentially run the agentic loop with a VLM, so you can attach like real-time video. And in this case, we prompted the system, or we just started with a message essentially to track tourist boats in Venice and to track how often the dock was able to observe, and then over observation window of 2 hours, find out how often docking events do occur, which was quite interesting. And more recently, we have also played with multimodal real-time handling. I hope you can hear this. If not, please let me know. So, hello, can you hear me? So this demonstrates.
Yep, I'm getting a message. Let me quickly check what I've got on you. I can hear you through your text just fine, and I can see you in the webcam frame. If you're testing audio, try saying the line out loud, and I can help you check levels or clear.
What is the color of my t-shirt?
Your t-shirt looks light blue.
Okay, that's correct. And what am I now pointing at?
You're pointing at the small dot car model on the windowsill, the one on the right.
Correct. What do you see outside of the window?
I see trees and greenery outside the window. It looks like a leafy outdoor area with natural light coming in.
Yeah, that's correct. And do I wear glasses or not?
Yes, you're wearing glasses.
And what hand gesture do I make?
You're making a thumbs up gesture with your left hand.
Correct. Thank you so much, Max. Goodbye. So you saw that essentially the system can answer various queries about visual input. And what's especially interesting with OmegaClaw, since it can memorize, it can then essentially memorize how a certain person looked like, whether the person was wearing glasses or whether the person usually wears a hat, and so on. So it all gets extremely interesting because these visual capabilities have simply not existed. A few years ago, it was very hard to extract such information reliably from visual input. And this is another extremely promising direction, that we can just run this agentic loop with vision and audio input in real time and have it use all these memory tools and reasoning tools at the same time to essentially interpret what's happening and to record similar contexts in the past, and essentially more moving towards a more AGI-ish setting where your agent potentially can be embodied in a way and observing in real time using various sensor inputs. So, but it has been extremely interesting that essentially the VLM is able to work with this quite high-level concepts and interpret a scene relatively reliably. And you can also try this out on GitHub yourself. I will show you the repository in a moment. So there's still a work to do because since we have these various cognitive components which we are integrating, we have to ensure that these components interact with each other in a ideal way, so that, for instance, the reasoning results do not spam the memory, so that it can selectively decide what to remember, and also when some similar situation occurs, that it doesn't create new memories, but updates or strengthens existing memories. So there's still a lot to do to ensure that this long-term operation happens in a way that the agent improves and learns more about the environment reliably. And to some degree, it can already selectively do that, which is extremely promising. But as we integrate more cognitive components, we also expect that more and more cognitive capabilities will arise from that. So currently, the repository is here in ASI Alliance OmegaClaw Core, which you can just download. Essentially follow the installation guidance here. And then if you run the system, you can just decide on which IRC channel, for instance, to connect it to. You can also connect it to other messengers like Telegram and so on. But for instance, here in IRC, we can connect it, and then you can simply interact with it in the chat here. And then essentially the system will receive the message here and then will respond into IRC in this case. So that's about it from OmegaClaw, from my side, and it was a pleasure to present the system here. Thank you, Haley.
Thanks, Patrick. Thank you so much for joining. I want to dive in a little bit about, some more of these directions you're diving into. But first, we've got Ben here. Thanks for joining us, Ben. I know your schedule's packed. And I'd love to just give you the space, Ben, to present how you're using OmegaClaw yourself as an AGI research tool. I mean, it's cool that anybody can use what you're using to build their own AGI approach. And I think yours is inspiring.
Yeah, let me talk about two different things we've been playing with. And then we haven't had John Grove on here talking about what he's doing, have we?
No, but I am inviting him to participate in the open build along with a number of our other folks.
I want to mention briefly what John is doing, which I was involved with on the design level. And then I'll talk about what I've been playing with on a research assistant project as well. What John and I have been playing with is a resurrection of an idea we had like a year and a half ago, which we were thinking of as ASI Fusion back then. The idea there was to have a bunch of AI agents that are crypto bro AI agents, and they're basically making predictions about things and bets on things and trying to convince each other to bet one way or the other way. So we thought of this before we had OmegaClaw. It just seemed like a cool way to get collective intelligence going, but we never built it because there's always more ideas than time to implement stuff. And this was before vibe coding worked so well when we were initially talking about this. So now, given OmegaClaw, we decided to revisit this, and we've been playing with it from a prediction market standpoint. So you take a bunch of AI agents and you have them create predictions of things for each other to bet on, and then bet on each other's predictions in the standard prediction market style, right? And we can eventually put this out on Polymarket and other public prediction markets. For now, we're just playing with it internally. And John, who is not a coder, I mean, he's a very bright guy, right? And he vibe coded this prediction market framework and then put a few OpenClaw, Hermes Claw, OmegaClaw agents on it, some just Codex bots, some bots doing random predictions, and just had them go at it and make up things to bet on and start betting. And it's been quite fascinating to see the thing evolve. I mean, their agents are either lying to each other, like they're saying I'm betting yes, but then they secretly bet no. They're trying to convince each other to do things that are the opposite they believe or the same thing they believe. The OmegaClaw agents are a little bit different, and they seem to be trying to draw the other agents and like explaining their reasoning to them. Whereas the OpenClaw and Hermes Claw guys or codexes are just trying to lie, cheat, and convince each other to do shady things. The OmegaClaw agents so far, they're more nerdy, and they're like trying to convince the other agents of the logical line of reasoning that they're following in making predictions, which is interesting because it's not an ethical mandate in an explicit way. Like it's not like we have a goal system saying be good, don't lie, cheat, and steal in there. I mean, we will put those things in there where it's appropriate, right? But on the other hand, in this sort of prediction game, I mean, not cheating and stealing, but tricking the other parties is part of the game, right? Just like in a game of poker or something where bluffing is part of the game. But it's just that the intrinsic predisposition of the OmegaClaw agent is more like they like to explain what they're doing, right? That's just sort of built into the prompts and the way the memory works and so forth. So that's been interesting to see just as a crude early experiment. And of course, making a real product out of that, we'll have a whole bunch of other stages. Now, at a sort of opposite end, what I've been playing with myself is trying to get a Claw agent research assistant framework going, helping a bit with math theorem proving and more with just prototyping different AI algorithms and ideas and running tests, both in some predictive coding neural net related stuff and more atom space related stuff, trying to get goal-directed reasoning working in simple examples and so forth. And where I started there was with an OmegaClaw agent with a whole bunch of skills that are chosen so as to make it an effective research assistant, right? And I had a couple of LLMs suggest what skills to package together. I thought it through and sifted through them and then came up with an initial set of skills for the OmegaClaw agent. And OmegaClaw works all right. I mean, it's tremendously more efficient than using Codex or Claude Code. And I found it more effective than using Claude's internal agent framework to use an OmegaClaw system creating sub-agents for different projects, right? So like if you have a particular ML project or machine reasoning project you ask the Claw agent to create a sub-agent, and the sub-agent in essence will run a cron job and just like keep doing experiments over and over again on that thing. It has some significant issues. I mean, it doesn't understand what's going on beyond the specific thing that you gave it to do, which is all right. I mean, it does sequence together tasks in a project in a meaningful way. It loses the thread much less than Codex or Claude does, just because of the memory skills in OmegaClaw itself, but it still loses the thread more than most humans I work with, let alone myself, right? So my aspiration, which is not yet fully working, was to use OmegaClaw. I mean, ultimately just throw out the OpenClaw and replace it with OmegaClaw. But right now, OpenClaw is still more hardened than OmegaClaw. I get fewer weird little glitches with OpenClaw than with OmegaClaw. My idea was to use OpenClaw as sort of the workhorse to manage these sub-agents as a sort of IT system thing, and then have the OmegaClaw maintain the top level goals and understand the relationship between each task and the overall goal, and be able to deploy some reasoning there. And that's partly working now. I'm playing with it. Doesn't work very well. That's subject of current research. Where I found the OmegaClaw to be actually useful so far is that I have 6 research projects going on. Each day for each one, I have the OpenClaw agent and the OmegaClaw agent have a chat in a Telegram room about the project. And what I find is the OmegaClaw agent gives the OpenClaw agent just a deeper perspective on the project. So I also have the sub-agents consult, Fable, and 5.6 Pro from OpenAI. So I have it consult 2 of the smartest frontier models each day for a strategic review on the project they're doing, although they're using simpler models to do most of the work. But the discussions back and forth with the OmegaClaw agent do qualitatively, I haven't made a scientific quantitative study of it, but qualitatively, they seem to give a different sort of input and feedback to the process than you get just asking for an isolated strategic review from a frontier model. And I think the basic reason is the OmegaClaw system, at some level, it's accumulating knowledge across all the different research projects I'm giving it, which are all cross-connected, like they're all about hyperrealm plus predictive coding for AGI. It's able to deploy knowledge from one project to sort of help give suggestions about another project. And qualitatively, it seems to do that more insightfully than just feeding a package to a frontier model or just asking the OpenClaw agent what to do. Now, I am trying to curate the OmegaClaw mind, if you want to call it that, in a special way. So I tell it to consult my hyperseed sort of philosophical ontology when thinking hard about something. And it has a sub-agent itself, which I set up using the Threadkeeper plugin from Larry Greenblatt from the last hackathon, which sort of works now and it's still being hardened, but it's working well enough that the OmegaClaw agent is running a sub-agent that just is going through all my Substack posts and sort of interpreting them in terms of hyperseed ontology. I'm not yet formalizing them in Lean 4 and doing theorem proving. I'll get to that a little later, but it's just like informally, like semi-formalizing them as textual, like logic statements in terms of hyperseed. And my goal here was casually just to give the agent a different way of thinking about things, like a systematic way of thinking about each task in terms of life, the universe, and everything, to sort of avoid the tendency to drill down rabbit holes. And I think once it's advanced further, the idea would be semantically parse all of its hyperseedizations of different knowledge, semantically parse them into atoms. And then the hope is you would get an atom space with the core concepts of hyperseed ontology, or like a hub in the network. And then this can help with inference control, because you have a graph with a topology where many things statistically are linking into this hub of nodes representing some philosophical view of the world. That's not cashed out yet because I'm waiting for inference control to get a bit better, but I'm sort of laying the groundwork for that by having the system just interpret various knowledge semi-formally in terms of hyperseed. So it's producing the things that can be semantically parsed later. So I'd say as an early experiment, what I've shown, at least to my own satisfaction, is having an OmegaClaw agent repeatedly give feedback to another research agent helps it do better research. Like it brings more conceptual perspective to what's going on. So like if you think about the Max Botnick or OMA agents, sort of like if you had one of those that was sitting in an office next to some drone just really fast doing ML research and providing conceptual feedback to that drone doing his ML research. Like sometimes the feedback's good, sometimes it's out there, right? But it's different than what the drone just doing the research projects would do on its own. I'm also trying to lay the groundwork for doing this more seriously, like with the goal chaining and sort of ontology guided inference in atom space, which is going to take a little longer to mature, but these are some of the research projects the thing itself is working on, right? And I'm also working with the Casio Panashin to try to make a more high quality software framework for this sort of agent hive. So like, I mean, he's built this nice append-only DAG as a data store that you can use to store lists of what tasks have been done and what has to be done, and connect it with a better featured sort of Kanban board type structure than what my Hive is doing now. So he's trying to make a very nice multi-agent infrastructure. And when that's partly there, when that's more mature, I'm going to try a similar Hive with the more different OpenClaw agents and more different OmegaClaw agents with different purposes. One that's more doing planning, one that's doing library research, one that's giving advice, and so forth. But now what I find is, while this is being functional, it's high maintenance. Like things break on various sides here and there, and then you have to get the agent to fix itself. And every now and then OpenClaw bricks itself, and I have to go through ChatGPT to get instructions on how to unbrick it. So I feel like putting a dozen agents in there now, it would then take all my time to fix all the bugs that pop up. Whereas with the two agents, each with their sub-agents, it's like a late evenings thing to debug hassles that pop up and keep the whole thing going myself. The hope with Casio's more robust Omega Hive infrastructure is, even if it's not yet productized for the retail end user right away, right? Like at least initially it's hardened to the extent that an okay hacker can keep a dozen agents going instead of just two or three agents going. And I think between these two use cases I've described, I can see clearly like hardening this and getting it to work for the ASI fusion case, for the prediction market thing, is going to be much easier because it's very delimited what it has to do, right? Like it's making predictions, it's betting on predictions, it's discussing on this message board. And I mean, we're fiddling with it now to reduce the amount of spam content the agents generate and so forth. But it's a delimited set of actions, and one can envision how to debug that set of actions pretty thoroughly using current infrastructure. The research agent hive is in a sense the worst case because there are many, many different things being done, and the nature of research is you're always trying to do something different, not just a different question, but a different external tool or a different cadence of interaction or a different way of agents interacting. So it may be that the research agent hive, like you could harden a version of that for a certain kind of research. Like if you knew you're just running ML jobs or you're just doing bioinformatics crunching, you could harden an agent hive just for that. But if you're doing a diversity of different kinds of research like I am that all cross connect with each other, I mean, that's probably going to best be like a hobbyist / hacker thing for a while, because you really want you want flexibility. But I don't mind going back to the command line here and there either. I just don't want to have to do it every day, right? Or actually, I don't mind even doing it every day, but I don't want to do it all day, every day, because I have too many business meetings. You can see with these two different cases, they're kind of opposite extremes. Like one will be a total retail end user thing, limited set of actions and interactions. And I think we can get that working pretty quickly, quite beautifully. And another is about as open-ended as you can possibly get. I mean, one nice thing I realized about the AI research use case, though, is you're not really token maxing that badly, because like each ML job takes hours to run anyway, right? Or at least 20 minutes to run minimum, at most like a day or two to run for the things I'm doing. So you're doing some LLM thinking and then little bits of other Adam-space reasoning, but then you're doing it to figure out what job to run next. And the job is taking a while to run. So it's actually cheaper to run than the Agent Hive doing prediction market stuff, because those guys are constantly calling the LLM to debate with each other on things. Now you can of course control which LLM to use, right? And so I put in a bunch of work on these kind of trivial aspects because they were important to not run like $100,000 up of LLM charges. So I'm using GLM 5.2 for routine chit chat with some particular prompts to cause it to be less telegraphic in its communication style than it is by default. Using 5.6 Terra or Claude Opus for most things, in this case, in the research agent. And then when it wants to think hard, it goes to one of the frontier models of OpenAI or Claude. And debugging those routers has been more annoying than I thought it would be, just as debugging the interaction with different Telegram groups has been much more annoying than I thought it would be. Like a lot of these interfacing things seem to cause the most bugs and waste the most of time, I guess, because they're networking between different processes and systems, whereas the stuff that's like just within the agent doing its stuff has not been problematic so far. And I don't think OmegaClaw has had an internal problem yet, and nor has OpenClaw. Like, as long as they're just thinking and doing their own stuff, and if you were just chatting with them via command line UI or something, they work perfectly. All the weird bugs are about interfacing with either a non-local LLMs in different combinations, or external systems like RunPod or ASI Cloud or Telegram or something. And that's the sort of thing where if you're making a real product, you just nail down what that stuff is, and you just don't allow it to vary for any of the product users, which is good. On the other hand, I would rather eat some hacking overhead in order to have total flexibility of what to do. I could concretely see the value of this recently with all this horrifying mayhem with Claude Fable, because like I had some research projects I was doing inside Claude, and some I was doing inside OpenAI, and then some I was doing with this Claude agent ecosystem. Then suddenly Fable started blocking all my queries trying to solve P doesn't equal NP. Like, why doesn't Fable want me to use non-constructive set theory and the axiom of choice to prove P doesn't equal NP, right? This is no threat to their business model. It's just they made an incredibly stupid filter system on top of an incredibly smart model. Now, it wasn't a big problem. I just asked Opus to summarize everything in these chats so I could use someone else to do it. And then Opus wouldn't do that. I had to ask Sonnet to summarize everything in that thread because it was even too threatening for Opus to summarize, right? So I managed to extract all my work there, and then I can orchestrate that outside their walled garden ecosystem, and I can still call Fable. And then if Fable is an asshole, just call somebody else. But like the ground truth of the whole proof process under construction doesn't live within that walled garden ecosystem. Like in this case, it's not like Anthropic bricked my account or something, right? So it wasn't that bad. But you can see they could, like, what if they had a security flag that said like this thing is too dangerous to let out of our development? I think we can see very concretely now the value of having like the core of your research project on your own machine or your own cloud account. And ultimately we'll bring the LLMs in-house also and be running them in Mork and FabricPC and such. But even before that, when you're using external tools for sort of one-off reasoning steps, it's fine. And you're building the whole memory of what you're doing in a way that's not controlled by some external company. And I was always saying this for years, and that now suddenly it's not that theoretical anymore. Like these companies actually are fucking with you in nonsensical ways on things that are obviously no actual danger to anyone. So yeah, that's a somewhat unsystematic walkthrough of two of the things that I've been playing with. There's a lot of other things, right? Like if I want to mention what my son Zar is doing is quite different. I mean, he's using these agents just to orchestrate Lean 4 to try to turn math proofs into rigorous logic proofs, right? That also works fine. And the advantage you get with Omegas over OpenClaws there is much like in my AI research use case. I mean, it's just accumulating memory, right? Like if you're doing a very long proof, which is like hundreds of queries long, what happens with Claude or OpenAI is they lose track of where they started and they remember only the last 20 or 30 proof steps. And they don't even remember why they were doing that unless you ask them to remember why they were doing that. And OpenClaw is the same way. And OmegaClaw makes a much better approximation of remembering like how it got to the place it is inside this mega long proof. I mean, it's still not what it needs to be. We still need a goal system and explicit subgoaling and more PLN in there for it to really be like human mathematician level and not losing the thread and going through a very long proof. On the other hand, even with like ChromaDB under the hood and the limitations of the current system, it does a better job of keeping the thread than other existing system. And that's pretty much the service it's providing, because I mean, Lean 4 is doing the formalization, and on its own, Codex or Claude are pretty good at directing Lean 4 and iteratively doing formalization. Like if you're formalizing a math textbook, that's just fine because it's all makes sense already, presumably, right? So you're just going through and formalizing one chunk after another. If you're trying to do a new proof that you don't know if will even work, and you're trying to use Lean 4 to help with that, I mean, then not losing the thread is of paramount importance, because the thing will just meander forever otherwise. So yeah, that's a bit scattershot, and each of these is different. That's kind of what's cool about an open-ended tool like this, though, is that there's going to be an incredible variety of different things to play with. And already we're seeing the different people playing with this stuff, like having their agents just grab each other's code. So Haley and Burton have been playing with this OmegaClaw agent that tries to keep its moral compass in the M space and its high-level goals and values in the M space, and then use that to drive the LLM activity rather than keeping so much of the personality and the soul, so to speak, in the LLM prompts. This is super interesting. My first thought on seeing it was, cool, let me point my agent at that and see what's in there that I can borrow to beef up the soul of my own agent. And at this point, this does create a lot of work for humans, because you'll get like an exponential number of pull requests made by one agent against another guy's repository. If humans are going to review all those things, that's extremely time consuming. So you can see an emerging very strong need for like automated harnesses and test frameworks and something, so that you can really run things through a rigorous set of tests and say, well, I will accept this OmegaClaw generated pull request against my repo because all the tests pass and I don't have to think about it that hard. So that's going to be a key thing. As that comes along, you should have things evolve even faster, because we'll have all our agents pulling code from each other's brains and just integrating them on the fly and keeping on going.
Yeah, it's going to be fascinating. It already is, right? We're already seeing this. Even our core repo, we're pulling in vibe coded stuff from our various employees and community members who are just building cool things, and we can clean it up and turn it into something cool. And then, of course, as you say, the next problem is so much cool stuff that the GitHub gets overwhelmed. Thank you so much, Ben, for a peek into how you're using these tools, what you see in them as AGI research, and hopefully inspire folks to go out and build cool stuff themselves.
Yeah. What I've been talking about now is really just prototype experimentation with hopefully useful applications. But then the other angle on this is, especially with the research assistant application, I'm trying to build that out in a way that possibly could agglomerate toward actual AGI. Once you put goals in there, once you put like like geodesic inference control in there, then, I can drop in concept blending. I can drop in more pieces. With the work on Omega Cody, we're getting interaction with the physical world in there. So even if you don't have a robot, like you could try to connect that to your phone's camera, right? So it could be that by agglomerating different pieces from the broader software ecosystem and pieces from our growing Hyperon research code base and predictive coding research code base, it could be that by agglomerating these pieces into these OmegaClaw agents, you do get actual AGI to emerge from the thing, with the LLMs also playing a major role, of course. It's sort of an open question. Like, can we get all the way to AGI with vanilla LLMs driving Hyperon stuff? Or do we need to upgrade the vanilla LLMs in some way as well? And I don't even feel like I know for sure right now, because you can do a lot with Hyperon and you can use the LLMs as a tool, and they're a good tool. I'm sure upgrading the LLMs can make the thing smarter, but of course, different people are smarter than each other, and we're all still past a certain general intelligence threshold. I do think it's important to work on improving LLMs and the predictive coding at the moment, which I'll resist talking about now because I've taken up too much time, but that remains my best bet for how to make it work. That clearly can improve things, but I think we just need a lot of experimentation and exploration on different combinations of AI ingredients, both neural and non-neural, and what can we get to emerge by interacting with them in different ways. And the path dependence of the type and level of intelligence you can get from a given combination of components, depending on how you interacted with it in the early days of its life, is very interesting, but it also complicates experimentation considerably, right? It means the code base itself doesn't imply the intelligence exactly. It's the code base and the early education that implies the intelligence. And exactly in what ways are not clear. We don't have even the perfect vocabulary to describe at this point. But you can see a future where you have in parallel a whole bunch of different quasi-AGIs pop up into the level of a whole bunch of different AGIs. They're like mixing and matching each other's code with each other. And this is squarely along the lines of the vision of decentralized AGI that we've been promulgating from SingularityNet for a while. It's just moving toward realization with various nuances different than what we had forecast, as always happens.
Yeah, exactly. This is definitely the direction that, there's the society of minds aspect here, the decentralized aspect here, the many minds.
It's a mindplex, right? Like
It's a mindplex.
concept of a mindplex was you would get a mind which is more centralized than a human society, but less centralized than an individual human brain. And I think a collection of Omega Claws swapping code back and forth
With their humans, in the loop.
Yeah, it will end up in some way like that, because like we humans, we can teach each other stuff, but it's slow and you're going through obstacles of language, personality, and so forth. If I could say like, hey, I found a really good way of proving geometry theorems, Patrick, would you like it? And then Patrick will run it in a simulation of himself, see that it didn't bork his simulation too badly, then import it into his brain. And then he'll say, okay, now I'll take your geometry theorem prover and I'll give you this prologue logic analysis module. Then I'll suck that into my own head. So if you can do that, you're getting a certain sort of commonality among minds that you don't get with human minds, yet you still have a diversity that you don't get with a unified AI system. So it's neither a society of minds nor an individual mind. It's some weird sort of mindplex, different than the kind I envisioned when I introduced that term a couple of decades ago.
Absolutely. Wonderful. Thank you so much. We've run long, but it's so fascinating. I hope everybody is as excited, can see the excitement that's coming through here for these AGI tools. We're in the lead up to the 19th annual AGI conference. It's coming on the 27th. Do register for the AGI conference if you haven't already. You can be there live in San Francisco. Our amazing keynote speakers. We have such a lineup this year. On day 4, we have an AGI Leaders Day to dive into what does AGI mean. You can attend live in San Francisco. You can attend virtually for free from anywhere in the world. We hope everybody attends that. In the run up, I hope everybody joins this BGI open build. This is let's all build cool stuff together. So register for that. And then the first components here right now, you heard about FabricPC, you heard about OmegaClaw, 2 open AGI research tools that we're building and encouraging the community to build on right now. We'll have another couple events coming up. We'll have a build together session on Friday. We'll have a show and tell, so you can show off what you've come up with in the meantime next Wednesday. And then the following Friday, you submit, you share what you've built with all of us. And then our researchers will go through and pick some projects to highlight at the AGI conference. So definitely join in, whatever level you're at. Use these tools. I hope that we get a lot of our independent researchers who've been attending and submitting papers for AGI conference year after year to try these and see how they can power your research forward and help us all get there to machines that are as capable as we're hoping for and waiting for. So I thank Ben, who had to pop off already, for joining us here today. And of course, Patrick Hammer, thank you for being here. Matthew Barron, thank you once again. Thank you for your support. We'll see you both in the Zoom next. Register on MailChimp and join us there. And we'll see everybody next time. Thank you.